I am taking the key points of the current carrying circular coil, solenoid and the toroid. So I will tell you some applications of these, all the three, the coil, solenoid and the toroid. The magnetic field is always maximum at the center of circular coil. सर्कुलर कॉइल, तो जैसे ये सर्कुलर कॉइल है, this is now carrying the current I like this. This is now center, then the center O. So this B naught equal to mu naught Ni upon 2a. A the radius of this coil. This is the maximum magnetic field. It is the maximum magnetic field. If we go away from this, the magnetic field will decrease. The magnetic field line at the center of coil is a straight line. And as we go away from this center to the circumference, the curvature increases. If suppose you are having two circular coils, suppose this is a circular coil, this is now center of this one, this is another circular coil, this carries the current in this way and this carries the current in this way. Then the magnetic field of these two is always mutually perpendicular. So the magnetic field of suppose this coil and this will have the magnetic field like this. This is now B1, this is now your B2. Then resultant of these two, this will be the V, and this is the angle between the magnetic fields of this one. So magnetic field of this coil will be in this direction. This is now your B1. And in this, because of this coil, the magnetic field will be in this direction, B2. This is now B1 and this is now B2. So because of this coil, so this B is equal to square root of B1 square plus B2 square. And now then this tan theta, this is equal to B2 upon B1. So theta equal to tan inverse B2 upon B1. So this is now resultant magnetic field and this is the angle between the two magnetic fields. If suppose B1 and B2 are equal, it means that both the coils are of the same radius and carrying the same current and they are concentric. Then the magnetic field will be if B1 is equal to B2, then equal to b dash, हम ये मान लेते हैं, let this is equal to b dash, then this b equal to root 2 b dash. This is not so much. And the angle tan theta, this is equal to b1 upon b1, so this theta equal to 45 degree, because both the values are equal, b1 and b2. At the point of inflection, the magnetic field varies linearly. So, this dV upon dx, this is equal to constant, and d2b upon dx square, this is equal to 0. These are the two conditions for the point of at the point of inflections. These are the conditions at point of inflections. And always remember that the distance between point of inflections is equal to the radius of the coil. The points of inflection lies on both sides of circular coil. Now the distance between them on both sides of the coil at a distance at a distance half of radius, half of radius. It means that suppose this is the circular coil, this is now circular coil carrying the current, this is now center, then one point will be here and another point will be here. This is P1 and P2, this is now center. Then this distance is equal to A by 2. And this distance is also equal to A by 2. A is what? The radius of the coil. This is the radius of the coil. A. Radius of coil. So distance between P1 and P2. The distance between P1 and P2, this is equal to A by 2 plus A by 2. This is equal to A. The radius of coil. Radius of coil. Now the magnetic field along the current carrying conductor is always 0. The magnetic field along the length of current carrying straight conductor is always 0. इसका मतलब क्या है कि जैसे ये आपने यहाँ पर कंडक्टर ले लिया, सपोज दिस इज द कंडक्टर, this is the conductor and this conductor carries the current. Suppose this is along its length, this is now conductor PQ and it carries a current I, and the magnetic field at this point, this is equal to 0. The magnetic field here, this is also equal to 0. Magnetic field here, this is also equal to 0. Magnetic field here, this is also equal to 0. Similarly, magnetic field here, this is also equal to 0. This is now also equal to 0. So magnetic field along the length of the conductor, ये कंडक्टर है इसमें, इसके along यहाँ चले जाएं, इस तरीके से इधर भी पीछे की तरफ आ जाएं, तो इसमें magnetic field इसके along जो होता है वो हमेशा 0 होता है. That is always 0. Now this is to this one, the magnetic pole pieces, magnetic poles on the ends of solenoid depends upon the direction of current passing through solenoid, So that is how suppose this is a solenoid, this we have a solenoid. This turn is inside to this one, that I have wound it like this, in this way. The current is going in this direction. Then the current here will be in this direction. If I see on this side, then current is appearing to be clockwise. Clockwise means this is now south pole, like this. This is now south pole. This will be south pole, and here the current is going out, so this is the north pole. This is now north pole. So this end will be the north pole. This is now your south pole. This is now your north pole. If suppose now I change the direction of current, then these poles will be changed. Suppose I have this this I take like this, and the current is suppose going in this way. This is now passing of the current. Then this, if I see on this side that current is going in this way, current is going in this. So what is happening? The current is going in, then this is appearing like this, then going here, and then finally this is coming out to be here. So this will be the south pole. This is now current is like this, south pole, and here the current is like this. So this is now north pole. So this will be north pole. So this is now north and this is now south. So if the direction of the current is interchanged, it changed in this coil, then this the polarity of this solenoid will change. So if suppose this is now south pole, then this will become north, and this is now north, then this will become south. So now what we have, suppose I have taken this binding like this one. If I take the binding by another way, this is now like this. This is in this way. Suppose this I carry the current. What that this is why I have taken it to be like this one. So here this is appearing clockwise. This is not clockwise. So when I am having this current is going like this one, then I will have this to be the north pole. This I give it. And now magnetic field. The magnetic field in the solenoid is given by B equal to mu naught Ni upon 2. This is now your cos phi 1 minus cos phi 2. This is the general formula. And how to apply this one? Suppose this is the solenoid. This I take the solenoid. This is the axis of the solenoid, and this is now suppose center O. And this end makes an angle with this one is suppose phi 1, and the other end makes an angle with this, that this angle is phi 2. The angle made by this end on this at the center is phi 1, and because of this end, this angle is phi 2. So that I have taken this cos phi 1 minus cos phi 2. So now you can see for ideal solenoid, what we have? Now this phi 1 is equal to 0 degree and phi 2 is equal to pi 1. This will go on increasing. So this angle will change. This phi 1 will become 0 and phi 2 will become pi. Then this B equal to mu naught Ni upon 2 into cos 0 minus cos pi. So this is equal to mu naught Ni upon 2. This is now your 1 minus, this is minus 1. So this is equal to mu naught Ni upon 2 into 1 plus 1. So this is equal to mu naught Ni into 2 upon 2. 2 and 2 cancel. So this B equal to mu naught Ni. This is so much. What we have that seen when I dragged the formula for the magnetic field at the center inside the solenoid, and I have taken that to be the ideal solenoid. If suppose we want to find the magnetic field at one end of the solenoid, then suppose this I take the point P1 and this I take point P1, this I take the point P2. Point P2. So magnetic field at the ends of the solenoid. Magnetic field at the ends of solenoid. Ends of the solenoid. What will happen if suppose I take this point P1, then at point P1 and P1, what will happen when this is now large one? Then when this point is brought here, then this pi y, this phi 2 will be equal to pi, and this phi equal to 0. So this phi 1 equal to 0, phi 2, this is equal to pi by 2. So now what will happen? This B equal to mu naught Ni upon 2 into cos 0 degree minus cos pi by 2. Cos pi by 2 is equal to 0. So this is equal to mu naught Ni upon 2. 1 minus 0. This is now your B. So this B equal to mu naught Ni upon 2. This is not so much. So this magnetic field is just half of this one. This magnetic field is half of this magnetic field. Similarly at NP2, what we will have? Now we will have this. If we are talking on this one, then this phi 1 will be pi by 2 and this phi 2 will be pi. So phi 1 is equal to pi by 2 and phi 2 is equal to pi. Then this B equal to mu naught Ni upon 2 into cos pi by 2 minus, this is now your cos pi, mu naught Ni upon 2. This is now 0 minus minus 1. This is now plus 1. So this will be equal to mu naught Ni upon 2. So this is equal to B. So again we are having this same expression. It means that the magnetic field at the ends of the solenoid is always half of the magnetic field at the center of the solenoid. It means that the magnetic field inside the solenoid is not the uniform magnetic field, but it changes from maximum to half value. So this maximum value is at the center, that we are having this mu naught Ni, and at the ends this we are having this mu naught Ni upon 2. It shows that magnetic field inside a solenoid is not uniform, but it changes from maximum value mu naught Ni to mu naught Ni upon 2. So at the center, this B is equal to mu naught Ni. At the ends, this B dash equal to mu naught Ni upon 2. So now ratio of these two, B upon B dash, is equal to 2 upon 1. This is not like this. Or B ratio B dash equal to 2 ratio 1. We can write it like this. Or B dash ratio B. This is 1 ratio 2. So magnetic field at the center of the solenoid is always maximum, and as we go from center to the ends, then the magnetic field decreases and it becomes half of the initial value. Now, the magnetic field outside the solenoid, is always zero. Now for solenoid, current carrying toroid Now this is of this shape that I can draw it to be here. This is now suppose This is in this way. It carries the current I. This is now center O. This is the axis. So the magnetic field outside this is equal to 0, and here this magnetic field is equal to 0. But inside this the magnetic field is not equal to 0. इसके अंदर मैग्नेटिक फील्ड 0 नहीं होता है, लेकिन इसके बाहर मैग्नेटिक फील्ड हमेशा 0 होता है। इस टोरॉइड को यहाँ पर ले लेंगे इस रीजन में तो भी मैग्नेटिक फील्ड 0 है, यहाँ पर ले लेंगे तो भी 0 है, लेकिन इसके अंदर रहेंगे तो मैग्नेटिक फील्ड का मान 0 नहीं होता है। द मैग्नेटिक फील्ड outside the toroid is 0. Inside the toroid magnetic field inside the toroid. Now this B is equal to mu naught Ni upon 2 pi r. ये वैल्यू इतनी होती है। तो यहाँ पर सब जगह 0 होता है इसमें, लेकिन इसके अंदर जो मैग्नेटिक फील्ड होता है वो इसमें कभी भी 0 नहीं होता है, इसकी वैल्यू इतनी होती है। So these were the some points which I have to tell you that about the magnetic field due to the current carrying coil, and that this solenoid and toroid. So thank you very much.